And it used to be 300. It used to be 299.
Due
It's
is
399.
this coming Wednesday. Okay. Homework number 5 due is Wednesday before class. And as you may know, please check your email account. Exam 1 start from this Wednesday. Okay. As I promised, I will show you one exam question. And as I mentioned, your homework number 5. Same question, but I will ask you different approaching, but it's the same question. So your homework number 5. Alright guys, come on. Then what's the last one?
Do what?
What's the last word? As I mentioned, homework number 5 exact question will be on the exam point. And so I ask you different approach, but conceptually, exact question will be the exam. Today I show you even more exam question. Why do you think I show you?
So we can start early.
You can start early. Well, my job is to encourage you to start now. My job is to make you work hard. And so, exam means what? You have to apply all yourself. No? Don't discuss with your friends. You don't talk. You try to ask some question. You are embarrassing your friend. So please, just do by yourself. So my job is to encourage you to work hard. Okay, let's look at it. Has anyone look at this documentation already? Not yet? No? Okay, let's look at together. Acetone production via dehydration of isopropanol. Isopropanol, in other words, is called isopropyl alcohol. Same name, same chemical. Isopropyl alcohol. You are asked to design to produce 50,000 metric tons per year of pharmaceutical grade acetone. 99.98%. But via the gas-based dehydration of isopropyl alcohol. But if you look at here, you want to produce pharmaceutical grade acetone 50,000 metric tons per year, and 1 year is 8,000 operating hours. 1 year, calendar hours, calendar hours, how many hours 1 year? 8,752 hours. But if you look at here, it's operating hours, it's 8,000 operating hours. Lillian, why?
Is it 40-hour week?
Chemical factory, we operate 24 hours. We operate 24 hours. We try to operate 365 days. But if you look at here, only 8,000 hours. Why?
Maintenance.
Maintenance. You shut down 8,000 hours means you shut down about 1 month for cleaning and maintenance. Yes? So we are not operating 365 days. We are only operating 333 days. 8,000 hours. Huh? Yes. But this information is available. How do you take care of, handle this information in Aspen simulation? That's kind of question. Now, general input specifications are given on the next page. Use PSRK property method. I give you property method so that when I grade your answers compared to my answers. So if this method is given, just use that method. No? Yes? Okay, good. The reaction is first order, okay, and occurs in the vapor phase over a catalyst. A lot of information is given, as I mentioned, read the sentence by sentence. There's some information in each sentence. Okay? This catalyst is available in the form of chilidated catalyst, and using packed bed reactor, we are going to use plug flow reactor. The main reaction for producing acetone is, as you can see, isopropyl alcohol is available by dehydration. We produce acetone, and reaction rate kinetics is given, which is based on catalytic reaction rate. That's also important information. Activation energy unit is given. The density of this catalyst is given, as you can see, 5,610 kilogram per cubic meter. It's called metal. Metal density is very high. Water is 1,000. So this one is about 5.6 times heavier than water. Okay, the OEDG is 0.5 porosity. Okay? And the packed bed reactor has a tube. So it looks like this reactor has tubes. How many tubes? 50 number of tubes. So this is multi-tube reactor. And this tube length is 10 feet, diameter is 1.5 inch. And this catalyst is zinc oxide. Yeah. Lots of information. Okay. Little pay attention to those units, inch and feet, number of tubes. Now, the first question is use global design spec to calculate the number of tubes in the reactor to achieve 99.9 weight percent purity acetone in the product system. And attach the screenshot of the result set on the DS-1 showing the final value of the answer. Yes. I ask you what we have learned so far. I'm not asking you any additional thing. So we all practiced this one. Let's look at it. Okay. Let's use suspend. Chemicals is electrically. And since we didn't look at this documentation, if I show you, if you go here, our main flow sheet looks like this. Okay? We have a mixer, plug flow reactor, flash separator, red column, pump, another mixer. We all run so fine, no problem. Input specifications, we practice this on how to use available information. So we are going to use the information. Ryan, Leah, good morning. What we are doing if you want to examine? Okay? Let me embarrass Ryan. What component do we have? Yeah. Huh? Acetone. At least you got some idea. Acetone. What else? Who is the savior for Ian and Ryan? Isopropyl alcohol. I like it. And acetone. Dehydration. We use hydrogen. So dehydration. Joe, this is not correct. What do we need to fix?
We gotta search up isopropyl.
Okay, so there's no component naming. You have to make sure you can see this component name. You bring some simulation file, you so define your component. Thinking my simulation got error like 5,000 error process. Don't make this kind of mistake. Yes? So isopropyl. Alcohol, if you use hyphen, it's easy to find. So make sure you found the component. Methods are specified, so use that method. It's called PSRK, predictive SRK method. So I choose PSRK. Go next. Estimate missing parameters. Oh, simple. Table generation activity. Who came later? Check. So I can read clearly. We have mixer, we have plug flow reactor, we have flash separator, and we have another mixer, red color, and pump. Pressure chamber. So maybe I can. Let's try to connect screen. attention, this red black column, where do I connect stream and where is the output stream? And recycle stream do not connect initially. Leave it open and do the simulation for stream. Okay. Let's name it. Another flow here. Our explain projects. Step 1. At the top. This one we get asset on the way. Okay. Our data stream. This is titled our power stream. Our recycle stream. Come. Okay. Now we have the information. Operational hour is 8,000 hours. One calendar year is 8,732 hours. Where do you think we can put that information? 8,000 hours operational hours. No idea? Guess, page.
Is there a way instead of like iterations, you can switch it to time?
No?
Okay.
Olivia.
Recording options?
Huh?
Recording options?
So our operational hour is 8,000 hours. We need to handle that information here. Where do you think we can look at it for that information? Type. Anyone?
What do you think you can do?
Sean. You guess. Come on, look at this. Right now.
Could you just like, if you have a flow rate, could you just multiply it by 8,000?
Maybe you can do it, but there's more difficult calculation.
Is there a unit set for it?
Set. Unit set.
Yeah.
Jay says unit set. Now you got some idea where. Look at this navigation here. No idea.
Set up.
Set up. Why not? No. You are setting something. No. This is very basic fundamental idea. But if I don't give you that idea, you cannot answer no good. Practice. How you develop this logic? You are setting something. Look at setup. Simple. But this idea of simple approach, if you don't know, you are like wandering everywhere here. Cannot find, waste time. We are setting something. Oh, let's look at setup. Yes. And then setup specifications. Okay, if you look at here, what do you see now? Operational here, you can see. So here, 8,766 hours, whole year operation. We have 1 month shutdown for maintenance. Our operational hour is 8,000 hours. You take care of here. Okay? Yes? Alright. Let's work on feed stream or input specifications are given. So I'm going to use that information quickly. Feed stream, 300 degrees Celsius, 35 bar. An isopropyl alcohol mass flow is given. Okay, 6,000 kPa. Next, we are working on flash separator, 40 degrees Celsius, 33 bar, valid basis, baked or liquid. Okay. We are working on plug flow reactor. Looks like temperature is given, so I will choose reactor with specified temperature. which is 300 degrees Celsius. You should pay attention here. Always reactor design is important. Configuration. We have multi-tube reactor. How many tubes? 15. Thank you. Natalie, answer loudly. Okay. Length. This tube length. 10 feet. Wonderful. So, pay attention to the diameter. 1.5 inch. The valid faces. Jay, what do you think? Wait only.
Catalyst.
Hmm?
With a catalyst.
Catalyst. What do you think? Hmm? Why? Isopropyl alcohol, acetone, those are liquid. Hydrogen, vapor. Maybe vapor, liquid is better. Okay? Yes? Let's go reaction. Now we need to define reaction. So reaction use navigation pane. Okay, new. We use power law. Okay. I am defining reaction. Isopropyl alcohol produce acetone and hydrogen. If you look at the reaction, come on, let's see. Value was missing. Olivia missed. Jack, give me come on, coefficient quickly. Too long. Then yes, Jay. Joe, can you help me? What are friends for? Okay, 1. Here. 1. Here. What else? Hmm? That's it. No, we are using kinetic. We need additional information. If it's equilibrium, that's enough. We are using kinetic. We need additional information here.
First order.
First order, First order. The information is given first order. So you have to put exponent 1 at least at reactant side. Okay? Good. Make sure. And then reaction type. Okay, kinetic equilibrium, we are using kinetic, so that's okay. Now, let's take care of kinetic. So if you look at here, we have only one reaction, reacting phase. Clear up. Gas, vapor, it's a given. The reaction occurs in the vapor phase. So, reacting phase, vapor. Rate basis. Lucia. Very simple.
I'm not sure either.
You're not sure either.
Oh, catalyst.
Catalyst, Catalyst. Over catalyst, Okay. If you don't do these steps, you will have wrong answer of negative 10 points. How about K value? Can anyone tell me the K value by looking at the documentation? Who can I rely on? Brian. You say no idea.
2.75.
Oh, I like it. 2.7549 10 to the 7. Okay, so 275.49. Brian, do you agree? Okay, good. Activation energy. Let's go quickly. Come on, why we are wasting time? Neil, are you sleeping? No idea? No. Harrison?
I don't look, so I'm not sure.
Documentation.
Negative 62,380.
62,380. Are you okay? Unit. Unit. Joule per mole or kilojoule per kilomole. Okay? reaction R-1. So I choose select R-1. Now here is critical step in. If you click next, you are skipping very critical step. Okay? That's the dilemma by using this next button. Without knowing what to do, you just click next, you are skipping one very critical step. What do you think is the critical step is?
The catalyst.
Catalyst. So if you look at it carefully here, okay, there is no red one here. So if you click next, you are skipping, but if you look at your catalyst tab, we have a catalyst. So do not skip this step in. And that's why I show you. Because we never learned this catalytic reaction. So I show you now. So catalyst present in reactor, yes. What information we have? Catalyst density, so particle density, which is equal to 5,610 kilogram per cubic meter, and voidage is given 0.5. Porosity is 0.5. This step is critical step. Now we are working on pump. Discharge pressure is given 35 bar. Efficiency not given, just leave it. We are working on columning. Number of stages 15. Condenser. What should we choose? Really?
Wait, I'm like one step behind. What
Okay.
did you put for?
Okay, can I really hear this?
Partial vapor liquid.
Wonderful. If you verify the condenser correct, no problem. Partial vapor liquid. Why? If you look at this left column, we have vapor stream, we have liquid stream. So partial vapor liquid. I like it. Reboiler, kettle reboiler, reflux ratio, mole basis is given 2, and if you look at it's called distillate to feed ratio, DF ratio, is given 0.995. As long as you choose distillate to feed ratio or distillate to bottom to feed ratio, then this feed basis become active. So you need to put some information. Feed basis. This is our feed stream. Distillate to feed ratio. So we have to choose distillate, which is acetone. Distillate to feed ratio. Okay. Feed stream stage number is 8. Condenser pressure is given 1.1 bar, and condenser temperature is given 45 degrees Celsius. We are ready to learn the simulation. What we are looking for? We are looking for mass flow and mass fraction. So I will choose mass flow, mass fraction. Cross finger. Oh my! No going nowhere. Natalie, our simulation is not over yet. What is our next step? Wonderful! Excellent. Excellent. See, Natalie is focusing, concentrating on this lecture. If you couldn't answer the lecture, you don't know what's going on. Told you, we did not connect the recycle stream yet, and Natalie gave us critical information. We have to connect the recycle stream. Okay? Great. Let me reset. As long as you connect the recycle stream, what do you think we need to do? TRC, I like it. Another is starting out. I can see. When I ask you a question, when you ask me a question, I can see how much you are working. You know, where is very honest thing, study or your skill or your level is very honest thing. Okay, tier stream. We have recycle stream, lead truck recycle. As long as we have recycle stream, define tier stream, increase number of iterations, and then maybe choose some other convergence lesson. We talked about those things. Oh my, I got no more. Let me highlight. Sean got 5,000 errors. Sean, I don't know what it is. I'm lucky, yes. Let's check our results. I don't know whether our simulation is over. Let's check our results. We are looking at acetone purity, pharmaceutical grade purity, 99.9%. But if you look at here, we got right 99.6% is not pharmaceutical grade. So our target is to make this value, this number, should be 99.9%. Okay? Now, if you look at documentation, the first question is, can anyone explain us what the first question is? Did you raise hand?
No, but I can read it.
Oh, can you read?
Yeah, we need a design spec, and we need the number of tubes in the reactor to achieve 99.9%.
Okay.
That's approved.
So, simply, question number 1 is looking for conduct or carry out design spec to find out how many tubes are necessary. We have reactor right now, plug flow reactor. We have tubes in it. So far we have 50 tubes. We only got 99.6%. Our target is to get 99.9%. Then how many tubes are necessary? That's the question. Yes, is it clear? Okay, so let's try to conduct. So we are looking for number of tubes. So follow, it says conduct global design specs. We conduct the global design spec here. Okay. Now define. What can we define? Come on, let's go quickly. Number of tubes. Another is, mass fraction of acetone. I agree. Define is our target, isn't it? Define. Our target, the purity is our target. We are looking for number of tubes, Jace. That's the vary. We vary. We are looking for number of tubes, we vary. Now define our target is more mass fraction of acetone. That's our target, isn't it? Okay. So that's a swing variable because acetone is a swing. And we are looking for mass fraction, not mole fraction. Mass fraction of acetone. Okay? Spec means what the variable we defined. Mass fraction of acetone. This one should be 99.9%. Tolerance may be 4 decimal point accuracy. And we vary number of tubes which we are looking for. Now, number of tubes is in the reactor is a block variable. Reactor is a block. So block variable, plug flow reactor, number of tubes is called N tube. Okay, this multi-tube, maybe I can put 10 to 200 somewhere there. We are looking for how many tubes are necessary to get 99.9% in. Go run the simulation, why not? We got 4 warnings. Okay? Now, if you look at, or let's go look at warnings, what warning says? Warning while checking input specification for varied variable in design spec warning. You are varying an integer variable. Number of 2 is integer variable, no decimal point. But if you use the design spec, the default is accuracy is 4 decimal point, continuous variable or real variable. As long as you use the design spec, you will get this kind of warning. Why? We are varying integer variable, but the design spec use real variable or continuous variable. So you will get this warning. Always, see? So if you look at here, another warning, it will be same. Simply you can see. Number of tube can be 51.9, of course not. Number of tube is integer variable. Right? Now, you have warning, 4 warnings. Oh, I don't like this So this may cause calculated gradient to be wrong and the convergence block to fail or give bad result. The warning says. So, oh, I am not satisfied. I'm not happy with this warning. Okay? How can we take care of this warning so that we are confident what we got so far? Design spec, as I said, the default is using real variable or double variable, continuous variable, or same, using decimal variable. We are varying number of tubes with integer variable. In that case, you can conduct sensitivity analysis and then you can set the increment as integer variable and then make sure your simulation is correct. So what that means, okay, I will hide this design space. Yes, Natalie.
Would changing like the step size to one?
No, that's the only for hasten the calculation, but they still use 4 decimal point calculation. So it's not going to work. But you can try. But the easiest way, you can hide that design spec and carry out sensitivity analysis and then make sure your simulation does not have any warning. So let me try to conduct the sensitivity analysis. Okay? So I'm going to conduct exactly the same thing, sensitivity analysis, to make sure my simulation is okay. Right? So by double checking the stepping. So sensitivity analysis, same thing. We vary, in this case, we vary number of stages. And we said 10 to 200. Now here, Natalie, here increment you can set 1 or 2 integer variables. If I set 1, there will be like 190 data point fixed time to calculate. 2, then about 95 data point with less calculation. But here is the point you can set as integer variable. Okay? Now define what we are looking for. We are looking for mass fraction of acetone. Okay, and then simply we can tabulate this step. If we don't have any warning or errors, then we are confident our simulation is correct. Yes? Okay, now let's look at the result. If you look at the result, let me see the curve, result curve. What we are looking at here, we are looking at acetone purity. So if you, okay, acetone purity, if you move around there, looks like, okay, can you see? Can you see those numbers? Who has eagle eyes? Brian, you may have eagle eyes. Wonderful. It says 74 something, 74 point something. Then we can get 99.9%. 74 point, what does the number mean? Number of tubes. So, we conduct this sensitivity analysis, no warning, no error. It says about 74 number of tubes. Now, can I deactivate? Okay, we are not doing sensitivity analysis. Let's go design spec and reveal. I hide it, now I reveal. Then I will redo the simulation. With the confidence our simulation is okay. Now we can check our result. Yes? So, the acetone purity should be 99.9%. So we got 99.9%. Yes? What we are looking for number of tubes. Then go to result section here, result folder. And we got the answer, 74. Double checking process. So even though in first question I asked, for example, if you look at here, use global design spec to calculate number of tubes. Even though I did not ask that the sensitivity analysis step, you put additional information, no problem. Always put more, practice more than I ask you. Alabama players, not anymore, as I mentioned. They practiced 8 hours per day, but their team mood is let's practice more. What we are working on here. So what I mean, print screen, no print screen, paint here, and you can click or crop this part like this, Control C, and attach here this, Control V. Yeah, this is what I mean. So attach the screenshot of the result. This is the result. Result tab on the design spec showing final value. So simply you attach this one. As I mentioned, if you did sensitivity analysis, okay, you can maybe put this sheet or describe. Oh, I have conducted the sensitivity analysis because of 4 warnings. Saying integer, you are using integer variable, something like that. Yes? Put additional description, no problem. You put less negative reduction of penalty. Let's go next question. With completed design step 1, and when you solve this exam question, go step by step. Always finish question number 1, and then go next question. Okay? So same thing with completed design spec 1. Use global design spec to determine how much isopropyl alcohol is required in feed stream to produce 50,000 metric tons per year of pharmaceutical grade acetone. In design spec 1, we already find out a pharmaceutical grade acetone purity. Okay. Now in design spec 2, let's see who is concentrating. Who can I rely on? Jared, I can rely on. Jared is working hard. Very quiet, working hard. Jared, question number 2. What we are asking for?
How many kilograms per hour of isopropyl alcohol we need to get 50,000 metric tons of acetone?
Wonderful. Okay, good. That's the question. So let's go conduct the design 2. And I can go new design 2. Yes. Okay, if you look at here, define spec vary. What we can define? What we can define here? What is our target we are looking for here? Amount of acetone. I like it. Amount of acetone. 50,000 metric ton, I think. So, amount of acetone, mass flow acetone. Okay? Great. Mass flow acetone. So, mass flow, we are looking for mass flow acetone. Now, pay attention here. Mass flow acetone, Olivia. How much? 50,000 metric ton per operational unit. And if you say 50,000 metric ton per year, we already defined 8,000 hours of operational hours. So 50,000 metric ton per operational year. If you look at this unit, pay attention. Okay, you can choose ton per operational year. If you look at here, tons per operational year, there are different units. So this is the skill set you need to develop. What's the difference? TONME and TONS.
One's
Okay,
one's a metric ton and one's a standard ton.
Short term. One is SI unit metric ton, another one is English unit ton. So there's a difference. So you choose this one. We are working on metric ton. TONME. simply I give you all answer. How nice I am. Don't you think so, Paige? Paige doesn't think so, right?
For operational, for operational.
This is the 50,000 metric ton per year.
There's also an operator year.
Yeah, what's the
Of course,
difference?
it's operational year.
Yeah.
Yes. Great. Focus. Yes. Now, spec is mass flow acetone. Okay. Our target is 50,000 metric ton. Now, target is 50,000 metric ton. Tolerance, you don't need to put like 4 decimal point accuracy. Okay, maybe 3 decimal point accuracy. If you put 4 decimal point accuracy, you may get some error or warning. Then tolerance, because your number, target number is very big number. What do we vary here? Isopropyl alcohol, that's isopropyl alcohol mass flow. That's what we are looking for. Not only already finished one question. And isopropyl alcohol is feed stream. Isopropyl alcohol initially was 6,000, so let's put 1,000 to 20,000. And I will reset. We will get more warning because of that integer variable. But we were confident that's not an issue, right? That's not an issue. So we can make sure our acetone purity is 99.9%. And how much isopropyl alcohol is necessary, you need to attach this one in. So what I mean, print to screen. Okay, crop this area, including result. Control C, and question number 2, Control V. This is what I need. And then don't attach it to big figure. We don't need to waste the space or paper. So okay, we'll make a little smaller size. About like that. Make it neat. And as you can see, I care about this number, this unit, and this number, this unit. Now, last question. Attach the resulting stream summary table with red circles indicating acetone mass fraction, mass flow in product stream. So, what does that mean? We have stream summary. I will attach stream summary table, stream table. Okay. Now you can attach this one, but I says red circles. Where do you need to put red circles? Yes, very good. Okay. I ask you, first we are looking for mass fractioning. So let's clear in. That's the mass fraction acetone, 99.9%. And what we are looking for? We are looking for isopropyl alcohol mass flow. We are looking for acetone production rate, and this one is isopropyl alcohol mass flow. Anyway, if I ask you to put red circles, please put red circles. As you can see, you just attach like this. It's very difficult to find. Sometimes you use a different name as from mine, very difficult to find. So please, the question is, there's a exact question. Read it carefully, and then submit what is requested. Please. Yeah. All right. And here, no, do not submit any unnecessary items such as like input summary. What does that mean? Some of you attach input summary. If you go here, this is input summary. It will like produce 7, 8 pages. Not submit it if it's not interested in. Okay? When you submit, I think it's a good exercise for you. Okay? When you submit this kind of work, good practice, try to put your name, for example, your name. Title is, for example, acetone production, something, and then you can put submitted by your name in, and then you will decorate it. Any questions? No? How is your homework going? Who finished the homework? Nobody yet? I told you it's a challenging question. Who started already? Okay, several. What do you feel? Chase. So you started, what do you feel so far?
Made the flow sheet, and I just need to know the design specs. And that's it.
Okay. Type. No? Joe.
I'm trying to figure out this like,
Joe, can you explain us to start with the homework question? What are our approach will be? What do you think? Jack? That's the what I asked, right? You need to carry out 2 sensitivity analysis, but before you do any sensitivity analysis, first thing, you must understand what the question is asking for. You have to understand first thing, and then develop the logic. How develop logic? As I said, develop logic is some drawings and sketch. Write down on your paper. Develop logic. Yes. That's more important than you directly go ask and then try to solve. It doesn't work. Yeah? So sketch paper, develop your logic first. Try to understand the first thing, what the question is asking for. Any questions? No? Okay. You can stop here. Wednesday, I will show you the design. I will not the solutions. So you can go through the exam, and hopefully maybe we can look at the homework on Friday. I don't know. But anyway,